Okay, my name is Steele Verzello, and I'm going to go through the Exam 2 written part. So let's go ahead and just start here. So for number 1, for A, what's the frequency of the non-disease allele in the human population? So the non-disease allele, ADPKD, affects 1 in 750 individuals. So since it's the allele, we're just going to take I should say for the non-disease allele, it affects the 749 out of 750, and the dominant. This is the autosomal dominant affects 1 in 750. So we're going through this for the frequency of the non-disease. You're going to take 749 divided by 750, and that will give you your allele frequency. For B, the frequency of the ADPKD allele in the human population is that 1 in 750 individuals, which is 0.0013. For C, what is the frequency of heterozygous individuals in the population? So we're going to use the Hardy-Weinberg part for this one, since we're talking about genotype now instead of just an individual allele frequency. So it's going to be that 2PQ portion, so we're going to take 2 times 0.9987 times 0.0013, we're going to get 0.0026. For D, out of a population of 1 million people, how many heterozygotes are expected? So you just take that frequency for your heterozygotes that we just calculated, multiply that by 1 million, and we should get right around 2,600 individuals that are expected heterozygotes. Okay, so for 2, 2A, the letter W indicates the phosphate group. Letter X indicates the sugar or the deoxyribose. Letter Y above indicates thymine, if we're talking about the pairs, or it's complementary, so A and T are complementary and G and C are complementary. So I'm assuming that on this one the Y is RT and the Z is guanine or RG. So for B, indicate the 5' and the 3' end of each DNA strand on the image above. So right here I have listed 5', 3', 5', 3' are opposites DNA. They go opposite of each other on that area there. So for C, on the image above, indicate the portion of the molecule that is considered to be the backbone. So the backbone is considered to be the phosphate and the sugar groups together, not just the phosphate or just the sugar, but both of them together. And on the image above for part D, indicate the portion of the molecule that gives DNA a net negative electrical charge. So that would be the phosphate groups that do that. Okay, so moving on to 3, let's see here, 3, so this one's a little bit more in depth, but for number 1, or for A, determine the allele arrangement for the heterozygous parent. So I have the heterozygous parent right here listed under 3A, so essentially it's a combination of the least numerous number of offspring. So that would just be the 8 right here and the 6, and essentially just writing that out. So for part B, determining the gene order of these 3 linked genes, you're going to want to take, oh sorry, I explained A wrong. It's the allele arrangement for the heterozygous parent is the combo of the most common offspring. So that's the 1773, the 1761 right there. So for part B, you're taking the DCOs, which are the double crossovers, are the least common, and you're writing that out. So I just wrote them straight out as they're written, and then you do the 2 other options, switching your middle allele, and that will give you the option to look at what happens when you do a double crossover to see which one would match your parent. So after doing the crossovers on this, I get K as the center allele, and then C, D, and E on either side. Doesn't matter how you do that. So Once we have that, we can start working on our linkage map. So the linkage map is essentially just finding the units distance away from that center allele for the CD and the E on this one. So you're going to organize them by single and double crossovers. So the double crossovers are the same for both of them. If you look, you have 8 and 6 and 8 and 6. And then when you take the single crossover, you're just basically moving this CD down here and this one up there, and then when you compare them to the ones that are here, if you have the 89 ebony cardinal wild type, that's what you get when you switch one of these for the top, and the other one on the bottom for the 97 is your kidney wild type. So I'm going to go ahead and add all those together, divide it by your total progeny that we have, which is 3,880. Multiply that by 100, and you get 0.0516 or 5.16 MUs. For the KE, same thing. You're going to do the single swap over for the E's, and then get those progeny numbers, which are 138 and 128, and add those together, divide it again by your total, multiply that by 100 to get your molecular units. So we got 0.5052 or 50.52 MUs. And then the actual linkage map drawn out is you have your CD ... 5.16 MUs, a couple more dots here, K dots, 50.52 MUs, a couple dots there, back to your E. So that is your linkage map. Okay, so for part D, it says calculate the interference. So to calculate interference, you're just going to take the frequency of each of those DCOs, and that is going to give you, using the sum rule, because it's both of them together, not just each individual. So go ahead and multiply those. You get 0.0261, and that will allow you to calculate for the expected number of DCOs. So you're going to take your total, multiply it by the frequency of your DCOs, and that should give you right around 101. I got 101.27. You're going to take your observed DCOs, which was very few here, which is comparing those two, but 8 plus 6, it gives us 14. And the interference formula is I equals 1 minus C, and C is our observed over our expected DCOs. So go ahead and take that, excuse me, go ahead and take that 14 divided by 101.27. You should get right in the ballpark of 0.1382. So once you have calculated your C, go ahead and plug that into your formula here. You get I equals 1 minus 0.1382, which gives you 0.8618. So multiply that to get by 100 to get your percentage, which is 86.18 of your double crossovers did not occur, which that looks about right because we expected 100 or so and we only got 14, so looks pretty good. Moving on to 4. So 4A, what's the frequency of the D allele in this population? This one's a little bit different than the first one since it's an autosomal recessive. The non-disease allele D, let's see, the syndrome affects 1 in 32,000 individuals in a certain population. In all cases, indicate your answers to 4 decimal places. So it's very similar to the previous one that we did. So the frequency for your allele is 1 divided by 32,000, which should give us 0.3125 times 10 to the negative 5th if we're doing the 4 decimal places. Scientific notation there. It's a very small amount. For B, we have the frequency of your capital D, which is the 31,999 divided by your 32,000. Should give you right in the ballpark of 0.9999. Okay, for C, we have the frequency of genotypes, so we're switching to the other part of the Hardy-Weinberg equation, where it's the p squared plus 2pq plus q squared equals 1. So this will be our p squared portion. So go ahead and take that frequency that we just figured out, the 0.9999, square that, should give you right around 0.9998. For D, the frequency of our heterozygous genotype in this population. That's going to be that 2PQ portion. So you go ahead and take 2 times 0.9999 times 0.3125 times 10 to the negative fifth. That should give you right around 0.6249 times 10 to the negative fourth. So that's what I got for my answers on this portion, and I hope they're all right.